is the following statement true, that for all a, b, and c that are integers, if a divides b and a divides c, then does a divide b² plus 2bc plus c²? Or in other words, does a divide b plus c all squared, right? That's what this is. So to figure out whether this is true or not, let's try and use an example to assume it's true and then try and prove that it might be true. So let's take the easiest example is going to be 2 divides 2 and 2 divides 4. I'm sticking with low numbers. I usually go with 4, 6, or 5 and 10, but the lower the numbers, I think the easier this is going to get. Or actually, no, let's choose 5 and 10. I think for this example, larger numbers shouldn't be that much more difficult to compute. So let's do 5 and 10 and 5 and 15. So what we're really asking is, does 5 divide 10 squared plus 2 times 10 times 15 plus 15 squared? Bad example. 15 squared is a difficult thing to compute. Let's go back to our example of 2 and 2. No, let's do 3, 6, and 3 and 9. I'm trying to have variety in my examples. Okay, 3, 6, 3, and 9. So we're asking, does 3 divide 6 squared plus 2 times 6 times 9 plus 9 squared? Okay, because we know that this is in fact the same as asking, does 3 divide 6 plus 9 all squared? We can quickly ask that, but before we do that, let's try and actually factor out a 3, because that's going to be our goal, to show that the right-hand side is going to be a multiple of what we have on the left, or the right-hand side can be written as what's on the left multiplied by an integer, or in this case, 3 multiplied by something in a bracket, which has to be an integer. So can we factor out a 3 here? I'm thinking so, because 6 is a multiple of 3, 9 is a multiple of 3, and these are definitely all multiples of 3. So we can quickly expand those to say this is the same as asking 6 multiplied by 6 plus 2 multiplied by 6 multiplied by 9 plus 9 multiplied by 9. We can definitely factor a 3 out here, because this is going to be the same as asking 3 multiplied by 2 times, 2 times 6 plus 2 times 2 times 9 plus 3 times 9. So clearly it's true because we can factor out a 3. So everything here is going to be an integer multiplied by 3. So it's true that it is divisible by 3. This should be more than enough proof. Just to be safe, I mean, you can obviously compute this 6 plus 9 all squared. 6 plus 9 is 15. That's going to be 15 squared. I'm not going to do that in my head. This is more than enough proof for me to assume that this statement is probably true. So let's go ahead and try and prove it. Okay, this is a for all statement, which means that we have to start with let. What do we let? We let a, b, and c be integers such that a divides b and a divides c and a cannot equal 0. I'm going to quickly erase this statement over here. Fantastic. All right, if you're wondering why I said cannot be 0, well, it's because obviously if a was 0, a divided by any integer b, or let's choose c because b looks like a 6, you're saying c can be written as 0 multiplied by some integer m. So if you want to find what that integer m is, you'd have to do c divided by 0, and you can't divide anything by 0, so m cannot be an integer. So that's why we have to say a can be any integer except for 0. Next. What do? We probably want to expand our definitions of what we mean by a divides b and a divides c. Well, what it means for a to divide b is that b can be written as a multiple of a, or b can be written as a multiplied by some integer. And c is a multiple of a, so c can be written as a multiplied by some integer. I'll choose g. Okay? Because the reader can only see what we're writing here, they know what a, b, and c are, their integers, but they don't know what k and g are, so we have to obviously define k and g. So we have to say where k and g are in fact integers. Fantastic. So now we have enough information to try and check this right-hand side and see if it can in fact be written as a multiplied by something in a huge bracket where everything in this bracket is going to be an integer. So let's go ahead and give that a shot. So we could say next b² plus 2bc plus c² can be written as ak² plus 2 times ak times ag plus ag all squared. Okay. I can factor an a out of this. Can't really factor an a out of this yet, although I probably can if I write both of those brackets. So I'm thinking if I just simply write ak multiplied by ak plus 2 times ak multiplied by ag plus ag multiplied by ag, right? And then here you can obviously factor out an a out of each of these. Take the a out and have it look like a multiplied by k multiplied by ak plus 2k times ag plus g multiplied by ag, where you would argue that this is in fact an integer. This is kind of ugly. I don't like doing this. So instead, I'm actually going to expand this and make it look a little bit nicer. But that's a perfectly valid way of doing this. I just prefer to expand brackets and use powers when it comes to these sorts of problems. So I'm going to say, this is the same as saying a² plus k² plus 2 times a² kg, right? If you expand these, the a's become a square, the k and g just multiply. Fantastic. And then plus a² g². There we go. Where this is the same as, we can now definitely factor out an a because all of these terms in the sum have an a. So we can say this is the same as saying a multiplied by, actually let me write this below. I don't think I'm going to have a good amount of space without becoming without skewing off to the right too much. So I'm going to instead say, give another arrow of then and say this is the same as saying a multiplied by ak² plus 2akg plus ag². Fantastic. And all that's left is for you to see that this is going to be an integer. Again, integers are all what a, k, and g are. Integers multiplied by themselves by integers are still going to be integers. 2 is an integer. The sum of any integers is still going to be an integer. So this is obviously going to be an integer. So we just have to explicitly state that, where ak² plus 2akg plus ag². Maybe it might be easier to actually introduce a variable. Usually I am against introducing variables, so I'm saying maybe you can say this is equal to m. Usually I would be against that, but because this is so long, it might be worth it so that when you're writing your conclusion, it'll be much quicker and easier instead of having to rewrite all this. But I'll stick with this for now. I'll say is in fact an integer. In conclusion, b² plus 2bc plus c² is a multiple of a given it's equal to ak², or my apologies, equal to a multiplied by ak² plus 2akg plus ag². So a does divide b² plus 2bc plus c². Fantastic. So this statement has been proven to be true. It might have actually been easier to go from here and say that b², or let me do this in a different color. We're finished the proof. This is perfectly fine. I'm now thinking it might have actually been smarter and quicker to simply argue b² plus 2bc plus c² is equal to b plus c squared, which is going to equal to what did I say? AK plus AG all squared. Oh, well, you would have still had to expand this, I think, so it wouldn't have helped us that much more. But there we go. We've now proven that this statement is in fact true.